Hello everyone. So this will be your last section of the unit number 2. So in this section, we are planning to discuss about work and energy, and especially work energy principle, and also energy conservation will be the most important part of the section. So now let's see what we have done so far. So now we discuss about the translational motion by using kinematics, and also translational motion by using Newton's law of motion, right? So translational motion means basically if you have an object, that object going to move in translational motion, that means it's not rotating and going, it's just moving as a translational motion. That will be a one-dimensional, or it can be a projectile. These all are, we call it as the translational motion. So now in this section, and also in next section that we're going to do it in unit 3, basically we're going to use the alternative analysis of translational motion by using energy and the momentum. So this energy and momentum concepts, they are actually remaining constant. Because of that, we're going to talk about energy conservation and also later on momentum conservation. Right. So this work in everywhere in our world, in subatomic space, everywhere this energy is a conserved quantity. Right? What is the energy? Energy is required for any sort of motion, right? So it's a scalar quantity, and it is assigned to an object or the system of object, right? That means I can think about one object, or I can think about the set of object, but we can use the energy to basically have a motion of the object. Right. So this energy can be changed from form to form. What that means is energy can transfer or change into another category of energy. Simple example is, that you get the sunlight. So that is the solar energy that we can get it into electricity at the home. So solar energy convert into electricity energy. So that kind of transfer energy is very important. Transfer means basically you carry the energy from one point to another point, right? And so so it's very important that we're going to talk about this energy that is actually very hard to define, but that is something that we require for us to do any sort of motion or any sort of work. We call it as the energy. So now in this chapter, we're going to talk about many categories of energy, but we basically going to talk about two energies that belong to mechanical energy. We call it as kinetic and potential energy. Okay, so we can discuss this over the section, but let me share my window first. So the concepts that we are talking, as I mentioned, it will be chapter 7 in your textbook. Okay, so chapter 7 in your textbook. Okay, so now let's move into my slides. Okay, so under this section, as I mentioned, main focus is talking about work done and work energy principle and the energy categories and also conservation of energy. So now first we'll take a look on what is the work done is. So work done actually in physics defined as a something that when you apply the force, if that object deform or something happen to that object, we call it as the work done. As example, if I have the pawn, if I apply the force, if this pawn move, that means something happened to this object. That case, I have the work done for this object, right? So similar to in here, in first case, you see that there is a wall, that person tried to push it, but nothing happened to the wall. Then we call it as zero work done. But in this case, object at least deform, although it does not move, part of that is deformed. Then we can call it as the work done. Okay, so that means there should be a measurable change to have the work done in physics. So now what is the definition of the work done? So simple example is you can think, now we talk about the forces, we talk about the displacement. Now if I have object, if I applied 1 Newton force to this object will say travel 1 meter. Now your object location is here. Now we are telling that we did the work done for this object, that work done will be 1 joule of work. So 1 joule of work. That means that is Newton times meter, because force times the distance will be the units of joule, right? So now this object move 1 meter by applying 1 Newton, then there is a work done 1 joule. Okay, that's the basic definition of the work done. So now work done in your class, we're going to use definitely because of the constant force. But in real life, your force is not always constant. In that case, we need to go to calculus to find the work done. But here in simple example, work done is defined as we're going to use the W for that. Remember that this will use for the later on for the some symbol watts, because in physics there are a lot of symbols we are reusing it but different names. In this case, uppercase W I am using for the work done. So work done will be equal to force and the displacement of the object. I'm going to use the D instead. It can be X direction, Y direction, or any other direction, and times angle between cosine, this is cosine, angle between F and D, I'm going to say theta. So now FD times cosine of theta, we call it as the work done. Now as soon as you see this formula, so cosine theta is the angle between force and the distance. In a simple example, in this case, you see that this lady is pulling by using the force this way. So this object will go to this distance. The angle between this and this will be basically this angle, right? So now as soon as you see this, you know that cosine of 0 is just 1, cosine of 90 is 0, right? So keep that in mind. Work done will be max when the cosine of theta is equal 1. That means theta equal 0. That means when you are pulling the object parallel to the force, that means if I have a force in this way, if the object moving in the same direction, then your work done is max, right? But if I apply the force in this way, but my friction is greater, then object going to move in this direction. Then what will happen? My applied force this way, but my object move in opposite direction. Now my angle will be 180 degrees. When it make 180 degrees, then you have the cosine of 180 is still 1, but it is a negative. Because of that, your work done will be negative in that case. This is where the work done max, right? When work done min will be 0, what will happen at that time? That means your theta angle is 90 degrees. What that means is, if you have an object and if you try to push this object upward direction, F, right? But your object is moving to the right direction due to some other forces or something else, right? So now this object moving in this direction, then your force is 90 degrees from the displacement. This is 90 degrees. Because of that, this force does not do any work, but there may be other forces doing the work, but perpendicular forces to the displacement don't do any work. Okay, that's the idea about the work done. It is still work done is a scalar quantity, but it can be a positive or negative because your object moving in the same direction as the force, or your object moving opposite direction as the force. That will give you the negative answer. Okay, so now exactly same thing I discussed. So friction always do the negative work because friction always opposite to the motion. And then centripetal force will never do the work. Reason is centripetal force is 90 degrees to the motion of the object. No work, because cosine 90 is 0. And in addition to that, you can have different forces doing different work. As an example, in this case, your tension force will do the positive work, but you know what will happen to the gravitational force. Gravitational force is staying in here. That force will do a negative work. At least one component of that will do a negative work. That will be a parallel to the plane component to the work, but perpendicular to the plane component does not do the work, right? So if there is more forces, definitely we need to find the net work by adding all the work done, including the negative work done and positive work done. Okay, that is the total net work done. Okay, so now let's move into the energy. After we discuss about the work done, energy actually needed to do the work done. That's what the definition of energy, that although I am not able to give you exact definition of the energy, that is basically needed to do the work, right, as we know. So now energy definitely going to measured by using same unit as work done. That means units of the energy will be still joule and is still a scalar quantity. Okay, and so now energy is conserved quantity. That we're going to talk about two conservation in your class. One is the energy conservation, other one is the momentum conservation, and we will talk about angular momentum conservation and those things, but still it is the momentum, right? So now as I mentioned earlier, energy is conserved, but it is able to transfer into different category of the energy, but you are not able to create or destroy the energy. So that is called it as energy conservation. Okay, so now, as you know, there are many forms of energy what we can have. In this class, we're going to focus into mechanical energy. So mechanical energy means basically there should be an object in motion, or there should be an object in some height, or there should be a spring that compress or stretch. That kind of energy, that basically the things that you are talking in your class will be belong to the mechanical energy. We're going to focus into mechanical energy in your class. But other than that, definitely there is solar energy, there are nuclear energy, there are electrical energy, that you're going to focus electrical energy into your physics 2 class. But there are many forms of energy that we have it in real life. Okay, so now we're going to move into the mechanical energy. So mechanical energy, I usually use the symbols. Mechanical energy, for this one textbook may use the different symbol, but I'm going to use mechanical energy as ME, right? So mechanical energy will be divided into two parts. So first one is kinetic energy. For kinetic energy, I will use K and E. And potential energy is the next one. I will use P and E. So we have kinetic energy and the potential energy. So these are the two energies that belong to mechanical energy, and we are going to talk in your class, right? So first one is the kinetic energy. So kinetic energy is defined as the energy of the motion. Energy of the motion, we call it as the kinetic energy. What that means? So that means there should be a motion of the object. That means there should be a velocity. And that object should have a mass. Then that object has the energy of the motion. That is the kinetic energy. That kinetic energy will be able to calculate by using half mass and velocity power 2. If you take mass in kilograms, velocity in meters per second, energy will be units of energy joule. Okay, that we know. So to get an understanding of this one, you can take the example that I have it in here. So I have a 2 kilogram kangaroo will hop 1 meters per second. Then if you calculate the kinetic energy, that will be 2 times 10 to the power 2 and divide by 2, just give you 1. So that will be 1 joule, right? So now if I have a kangaroo, we'll say mom. So mom has 4 kilogram, but is still moving with same velocity. Then if you calculate the kinetic energy, because of the mass is double, your kinetic energy seems to be double, right? So now in the last example is still the son, 2 kilograms, but he jumping now 2 meters per second. Now your velocity seems double from the first case, but your energy is now 4 times of the first case. Why? Because this power 2, never ever forget about this power 2. It will get the squared of the velocity. Okay. Okay, so now next one is the potential energy. So potential energy is defined as the energy of the position, right? That means, as example, to sit on the chair on the this place that I am sitting, or you are sitting on the chair, so you have potential energy because you are in some height, right? Similar to that, if my phone is in somewhere here, then I have a potential energy of this object because of the position of the object. So now how to calculate that potential energy? That will be basically your force of gravity of this object, that means mass times g. And then you're going to take the vertical height, wherever you're going to decide potential energy 0 point. So now potential energy, important information is you need to define the potential energy 0 point, then you're going to keep consist with that throughout your problem. That means you cannot change the potential energy 0 point time to time. So you need to define it. Or ground is my potential energy 0. Or in this height is my potential energy 0. Right? Then according to that, when the object is changed in the position, then you can calculate the potential energy by using force of gravity times the vertical height. So that is, we call it as the potential energy. So potential energy of the object, we can write it as, I'm going to write it that in here, this is the category that I am talking, force of gravity times, force of gravity is this one, and the vertical height h. So that is the gravitational potential energy. Or because of the gravity, there is potential energy. That is called it as gravitational potential energy. So now this potential energy is under, you remember that it is under mechanical energy, but potential energy we're going to discuss under 2 categories in your class. One is gravitational potential. I'm not going to write it. G for the gravitational potential energy. That is what that I talked right now. This is we can calculate by using mg and the vertical height. So now another category of that is spring potential energy. Spring potential energy. Spring potential energy. That means I should have a spring to have the potential energy. So now if there is a spring that have the potential energy, because that spring store the energy because of the stretch and the compress, that energy we call it as the spring potential energy. That will be equal to, spring potential energy will be equal to half spring constant times displacement of the spring. That means if I have a equilibrium position of the spring somewhere here, if I drag it, spring will be here, then displacement will be this much. You remember that the Hooke's law that we discussed, that displacement from the equilibrium position is the x. Okay, so now we talk about 3 energies under mechanical energy. First one is kinetic energy. Kinetic energy will be half mass velocity squared. So there is no direction. Kinetic energy is always a positive value. It is measured by using joules, right? And then we talk about the potential energy under 2 categories. One is gravitational potential energy. We can calculate because of the height of the object. It's important that you select the potential energy 0 according to your problem. So after that, your potential energy of the object from that 0 point will be force of gravity times the vertical height of the object from the potential energy zero. And then second category of the potential energy we discuss is spring potential energy. Your spring can be stretched or compressed, but wherever your object, your spring is stretched or compressed, it doesn't matter which direction. What matter is distance from your equilibrium to compress or stretch. So take that displacement and then you're going to do half times spring constant times displacement power 2. So now this value will never be a negative value. So it will be a positive value measured in joules. Only gravitational potential energy is possible to be negative because the reason is if you choose the potential energy zero in this place, if my object is in somewhere here, then your potential energy zero here, then if this one is mg, if this height is h, then this object has the mgh positive potential energy. But if I have the object in here, if this one is potential energy zero, then I still have mg, that is the force of gravity, but the height that I have it now negative direction. Because of that, this one is negative mgh. This is positive mgh with respect to this. This is negative mgh with respect to your potential energy 0.0. Other than that, kinetic energy and the spring potential energy will be always a positive value. Okay, so now again explaining these things, exactly that what I did in the potential energy explanation. And spring potential energy, this is what I talked about earlier, half times k and x to the power 2, right? So now we're going to move into the little bit about to get an understanding about the work done principle, right? So now this work done principle actually should be able to understand if you really know what kind of forces that we are working with. Because of that, there are usually conservative and non-conservative definition of the forces, right? So now what is the conservative means? Basically, that means if you move the object like a gravitational force, that it doesn't matter which direction you move, which format that you're going to move, with which path you're going to move, so that will be still a same. So that is called it as a conservative forces, right? That means basically your work done is independent of the path you select. So that is what the conservative means. What is the non-conservative means? Most of the forces we have non-conservative. Simple example is friction or air resistance. So friction, if you choose the path on the paper going from here to here, but if you choose the metal path going from here to here, then you have a different work done because of the friction effect to your work done, that will lose the little energy because of the heating of rubbing objects, or sometimes sound will release the energy. Because of that, your work done will be different by traveling in different path. Those are, we call it as non-conservative forces. Okay, so now conservative forces example in your class, we discuss about the gravitational force and we discuss about the spring force. These two we can take it as conservative forces, but friction force, drag force, those are non-conservative forces. Okay, so keep that in mind. So now we're going to move into the work done principle. So now this is, I'm going to talk about the conservative forces. So, so work done for the conservative forces will be equal to 0. That means net work done for the conservative forces will be equal to 0. So that means work done will be, write it as change of, what it is delta means? Delta, as I mentioned, always it is a change of something. Delta we use for the change of something. Okay, change of. So change of, in this case, change of kinetic energy or change of potential energy. Change of kinetic energy means kinetic energy final minus kinetic energy initial. change of potential energy means potential energy final place minus potential energy initial place. Always final minus initial is the change of something. So now in conservative forces, your net work done will be equal to 0. That will show you basically change of kinetic energy plus change of potential energy equal to 0. In other way, change of kinetic energy is equal negative change of potential energy. That's what it means in here. In other way, change of kinetic energy is equal to negative change of potential energy. Negative change of potential energy. So, right. So that means, so we can write the work done by using two ways. One is work done will be just change of kinetic energy. Other way is work done is negative change of kinetic energy, right? So now in conservative cases, if you add them together, that will be 0. So that is what the basically where the energy conservation coming from, that I'm going to talk in a minute. But now work done for the non-conservative forces will not be equal to 0. It is still change of kinetic energy plus change of potential energy, but it is not equal to 0. That means I need to do some kind of energy transfer, because of that path taken will make a different work in that case. In that case, I need to consider that little differently than the conservative cases. Okay. So now we are going to move into the energy conservation principle. So now to learn that, we may need to understand the types of systems we have, because the energy conservation that we're going to say is isolated system. We're going to talk about the isolated system because many of the systems are non-isolated. So what is the isolated system mean? So isolated system means basically this. So energy does not cross the boundaries of the system, and total energy of the system is a constant. Those we call it as the isolated system. For those isolated system, we can write the conservation of energy principle that will work for the isolated system. If it is non-isolated system, we need to do some modification of the conservation of energy. We are working with isolated system. Keep that in mind. Okay. So when I start about the energy, I mentioned that energy can be transferred, but not create or not destroy. So this transfer of energy can be anything. So that can be transfer energy by applying the force, that can be a work that we discussed, and it can be a mechanical wave, it can be a matter transfer, it can be electrical transmission or electromagnetic radiation. What different kind of transformations can happen of the energy, right? So, but we're going to move into the isolated system and talk about what is this energy conservation is. So now here it's very important, energy conservation, that in words, energy is constant, is working for conservative and non-conservative both, but non-conservative case, I need to take care the energy loss because of the friction or because of the path it will take, right? Other than that, in both cases, we can use the energy conservation. But in conservative case, you remember that I mentioned that in conservative case, your net work done will be 0 because of that change of kinetic energy plus change of potential energy equals 0. So now energies that we are discussing is kinetic and potential, obviously, and change of kinetic energy means kinetic energy final minus initial, or number 2 minus number 1, and potential energy difference, number 2 potential energy minus number 1 potential energy. I basically replace these two with this and these two with this, right? By using the change of something definition. So now what I can say, I can just exchange the things. I know that total energy I will be able to write by using kinetic energy plus potential energy. Now I bring the kinetic energy 2 and potential energy 2 into one side, and kinetic energy 1 and potential energy one into others. I take a paper and do the math, very simple math, exchanging the things left and right. And then this whole thing is energy final, this whole thing is energy initial. Because of that, I will be able to write this concept that we call it as energy conservation. So energy conservation. If you choose any 2 points of the process, you can say the energy at this position is exactly equal to the energy at this position. These two keep constant. That's what the energy conservation means if it is a conservative pose. Okay, so now non-conservative poses also I can use it. Only different is I have a work done because of the non-conservative pose. That work done, I have a kind of energy loss because of that. Because of that reason, I need to use exactly energy conservation as I have, but by subtracting the loss of energy because of the moving on the path. So initial energy is there, but I am losing some energy. When I come to the final energy is equal. Initial energy minus the loss, that will be my final energy. Okay, so that's the energy conservation. Okay, so this concept is very, very powerful and very easy to solve the problem, like kinematics problem that you solve. You can use the energy conservation because there is no actually the vector information in here, because we can use the scalar quantities and keep track on the energy conservation. Then you will be easy to develop what you want to find it out. So this is the in words, what is the energy conservation means. Basically, energy will not create or destroy, but energy will transfer from one form to another form. That is what we call it as energy conservation. Okay, so now let's think about this example, because we have done this many, many times by using kinematics. So you have object at the top, and then you're going to drop the object. Now what will happen at this whole top point? You're going to drop it. That means your velocity is 0. When it drops, velocities keep increasing, as we know, and displacement will be keep increasing in downward direction if you start with the origin, right? So now by forgetting about the displacement and the velocity and those things, you can think about by using the energy. Now if it is starting on the ground, if my object is somewhere here, then the potential energy of this object is maximum at this place. Then when it go down, potential energies keep decreasing. Why that happen? Because your vertical height is keep decreasing with respect to your potential energy 0 point. This is maximum, keep decreasing. That's what happened to your potential energy bar chart. You see here? That means I choose the potential energy 0 at this place. Okay. So now what will happen to the kinetic energy at the top? It doesn't matter where the potential energy is 0 for the kinetic energy. Kinetic energy matters with the mass times velocity squared. So now at this point, what is my velocity? It is 0 because you can drop it, right? So velocity is 0. That means your kinetic energy is 0. Now you drop in the object. What will happen to the velocity? Keep increasing. When it keep increasing, your bar chart in your kinetic energy is increasing because of velocity increase. So kinetic energy start with 0, it will keep increasing. So now important thing you need to check. At the top, all energy is potential energy. On the bottom, all energy is kinetic energy. What happened to that potential energy? It convert into kinetic energy at the bottom. But your total energy, if you add these two energies, you see that the blue bar chart and the red bar chart, if you add the heights of these two together, each point, these will be the same. That's what the energy conservation means. Okay, and another example is here. So you see that in the track that the cart start with initial velocity 0, then what you have it in kinetic energy will be 0 because that is depend on the velocity. So, but in this point, if I take the potential energy 0 at all the way here, then my potential energy maximum will be at this height. That's why I have this much of potential energy. right? Now, when the car going down on the hill, then you will see your kinetic energy keep increasing. At the bottom, my kinetic energy is equal to the what I have it in the potential energy initial. So potential energy turned into 0. That means your whole potential energy at the top convert into the kinetic energy at the bottom. Okay. If there is no friction, in this case, I consider it as conservative. Okay, so you guys going to do a lot of problems in your recitation session, but this problem I'm going to show you very simple example in here. If the initial height of the rock is 5 meters, calculate the rock velocity when it fallen 1 meter above the ground. You remember that this problem we will be able to use the kinematics equation, especially the third kinematics equation that I can use, and I can find the velocity at the bottom, but it will take few steps. And also you need to think about the direction of each parameters we use in kinematics. But here you'll see it is energy. What it's saying is, so you're going to start with potential energy 0. You're going to define wherever it is, it doesn't matter, but you need to keep consist with that. So now this is the height that we have. I'm going to call it as h, height from that place. So now first thing you're going to do is labeling your position. So because energy conservation has 1 and 2 position that you can use anywhere according to the given problem. In this case, I definitely can choose, this is where that I'm going to start the object. This is where that I'm going to find the velocity, final position. So now, after you write that, close to that, write your kinetic energy initial and write your kinetic potential energy initial at that place. The drawing is very important part in your class, right? So I'm giving points for those drawings, cartoons and things. So exactly follow what you are doing in your station and also the lecture. So kinetic energy initial will be how much? It is half times mass times initial velocity power 2. But since I'm going to drop the object, there is no kinetic energy initial, right? So potential energy at this point is force of gravity times the h. Okay, so now at final position, kinetic energy final will be equal half mass of the object and v final that I need to find it out. So I don't know yet, but your potential energy at this point, we already defined this point potential energy 0, because of that it will be equal to 0, right? So now you're going to use the energy conservation. What is the energy conservation is? E, wherever you choose as 1, E initial will be equal to E final, right? So now E initial is what you talk about is kinetic energy initial plus potential energy initial. Write these steps, each question, okay? So that will be easy for you to understand. So kinetic energy final plus potential energy final. So now I don't have the spin in here. If you have a spin, you definitely need to use the spin potential energy too. Okay. So now since the kinetic energy 0, I can make it 0 all the way, and potential energy final is 0. Now what I have is mgh is equal to kinetic energy final, that will be half mass and velocity final square. So now m will be cancelled out, right? So now v final, solve for v final is equal to 2 times g and h and root, and then you're going to plug the values. You will be able to find the v final. Okay. So remember that in kinematics, you need to use the third equation. You're going to use it and see what will happen. You definitely should get the same answer. But it is very convenient to use the energy conservation. Okay, so this section we're going to use energy conservation problem, but you can use the kinematics, but don't use it in this worksheet or the homework, because we're going to focus into energy conservation in this section. Okay. Okay, so last item I have is the power. So it's very important that power is not energy. right? Power is defined as energy per unit time or rate of change of work done. We call it as the power. Okay, how do you understand that? Easy thing is you have a hill, somebody can walk on the hill, somebody can run on the hill, right? When the running person will reach the top at first because it will take less time. When you have less time, then your power will be greater for that case. That's the definition of, that's how you understand the power. But these both person have the same work done because vertical height they are traveling is the same. Same work done, but only different is running person take less time than the walking person. Because of that, they have different power. That's the definition of the power. So power will be work done per unit time. That means units, joule per second. That unit we call it as watts. That's where that we use the W again, uppercase W, to symbolize the SI units of the power. Okay, I think that's it for this section. I will stop here.